Okay, so we ended last lecture by going over the postulates of quantum mechanics, and at this point, you know everything that there is to know about quantum mechanics. We'll continue to field theory. Some of you will do string theory. Doesn't matter. The postulates don't change. So basically we could have closed the course at this point because you know everything that is needed in order to do quantum mechanics. Nevertheless, we will now go through a few examples and continue to expand the theoretical basis of quantum mechanics. And the first thing that we're going to do today is a very famous experiment that we'll go over in details, and it will give us an example on basically how we construct the Hilbert space of a system, how do we treat the wave function, how do we measure all kinds of physical relevant operators, what is the influence of measurement, and so on and so forth. Okay, so the experiment is known as Stern-Gerlach experiment, and it is used as an example for a lot of things in physics for the simple reason that it's basically very simple. Okay, we have seen that basically we have to define a space with the different states the system can be in. Now a state that has only one state is boring, nothing can happen there. So the most simple state that we can think about is something with two possibilities, and this is a Stern-Gerlach experiment. So what is done in the Stern-Gerlach experiment? Basically, you have some source of atoms. You have a magnetic field. So north, south. This is actually 90 degrees. The particles emerge from here, go to the right, there's a screen here, and at the point where the atom meets the screen, it's deposited on it. So you get a layer of these atoms on the screen. You can run your experiment for a given amount of time and look at the screen. So what is expected? In this experiment, we don't care about the velocity, we don't care about the trajectory. The only thing that we come at the end of the experiment, we come and look at the screen. Now, if this particle had no magnetic moment, it will hit the screen exactly opposite to this opening in this box at its source, and we'll get here a small smudge of these atoms. Okay, now if we're using an atom that has a magnetic moment, we have no control on what is the direction of the magnetic moment. So one particle comes out with the magnetic moment in this direction, the other one comes out with a magnetic moment in another direction, and the interaction between the magnetic moment of the particle and the magnetic field pushes it up or down. You know that the interaction between a magnetic field and a magnetic moment is just a dot product between them. So after some time, you're supposed to come and look at the screen and see some smudge of hit points where this atom hit the screen.
As long as the field is inhomogeneous, right? Because if it's homogeneous, you will...
That's why I draw it as an inhomogeneous, but I didn't want to go into this detail. Conceptually, it's enough to know that there will be some interaction between the field and the moment, and this will move the particle up or down to some degree. And you are right, one has to write the form of the field, and if it's homogeneous, it has no influence, and if it's non-homogeneous, it will have. Therefore, the structure of the magnet is not two flat magnets, but this form, so I drew it correctly, but I don't want to go into the detail. Instead, I want to take the simplest model, simplest systems that we can think about, and for that, I don't want to go into the details. Okay, so Stern-Gerlach performed this experiment, and to their surprise, instead of seeing this smudge, they saw 2 points. As if this atom could have its magnetic moment only in 2 directions, relative, let's call it to the Z directions. There's only 2 possibilities. Now, this is not a completely new concept in quantum mechanics or in the old quantum mechanics. Probably in modern physics, you know that certain particles, let's say an electron, has a spin of half, and a spin of half means that it has only 2 directions compared to a given direction in space. Okay, so why is the name spin? And I have some new clips that is handling this problem of spin and then going on to Bell inequalities and entanglement, which is not covered in this course, but it's covered in these clips because it's interesting, modern, and nice to go into. But basically, for now, all I need to know is that this particle has 2 possibilities of magnetic moment, which I can call up or down, half and minus half, 1 or minus 1. All of them are used. Why it's called spin? Because in the old days, they knew that an electron has this magnetic moment, and now, how could an electron have a magnetic moment? Someone has an idea? What creates a magnetic field?
Moving current.
Moving charge.
Right, the current.
Moving charge. That's the only way we know how to create a magnetic field. Now, the electron has a magnetic moment even if it's standing still. So from where is this magnetic moment? So in the beginning of the 20th century, they thought about an electron as some rigid ball covered with charge. If it spins, it will have current. This current will create a magnetic moment. Okay, we explained everything, except that it's totally wrong. for a lot of reasons. One reason is, as we think about the electron nowadays, it's a point particle. A point particle can't spin. It's meaningless. Second, even if you claim that the electron is not a point contact, it's really a hard sphere. But it has to be smaller than some radius, because experiments have been performed up till this radius, and we haven't seen this radius. Then, in order to spin around quick enough to create the magnetic moment that is measured, it should spin quicker than the speed of light. Not possible. And it ended out with the Dirac equations that perhaps I mentioned in the beginning of the course, that you have a quantum degree of freedom that is coupled to the magnetic field and acts as a spin, as a magnetic moment, and it comes out from relativity, but not a simple mechanistic picture of a ball spin. Now, why does it have only two possible directions? Well, this has very much to do with properties of angular momentum that would have gone into this course towards the end. Unfortunately, this year probably won't get there because of the shortening of the course. And there we would have proved, and I hope you will prove in the next course in quantum mechanics, that the only possible degrees results that you can get are either integer or half integer numbers. So spin half will give you two results, half and minus half. Spin 1 will give you three results, 1, 0, minus 1. Spin 3 half will give you 3 half, half, minus half, and minus 3 half, 2, 5 results, and so on and so forth. You're aware, perhaps you're aware of it also in hydrogen atom. It has it. So spin, although it has nothing to do with physical spinning, has a similar mathematical structure to angular momentum. So of course the name spin is perhaps not so bad. Anyway, all of that is in the future. At the moment, we have a result of a measurement, and what we know, we have two states of the system. So, without knowing anything, and limiting ourselves to the measurement of the magnetic moment. I don't care about the position of the electron, I don't care about the velocity of the electron. I'm not measuring it. I'm measuring only, did it end up here or here? Then I know that I have a Hilbert space with two possible basis vectors. Why? Because I have two results. That's all I measure, and I know that each result corresponds to some eigenvalue of some operator that gives me the result according to the postulates of quantum mechanics. So I know I have here a Hilbert space of size 2. So first thing I learned from it is n equal 2. For a space of 2, how many basis vectors do I need? 2. So I can write it down as there are 2 basis vectors. I could write it down in this way. I could write there instead, which is spin up and spin down. I could have written half and minus half. Could have written 1 and minus 1. It's my prerogative. It's just how I denote these states. The important thing is that I have 2 states. Okay, question still here. Now you'll see all of it, all the different symbols in the literature, all of them are equivalent. It's just convenience or taste or whatever you call it. Okay. So I have the wave vectors. What do I mean by we have the wave vectors? If I want to describe the wave function of the particle, all I need for it and I have a full description of the system, right? By definition. We said that all that we can know about the system is in the wave function. The wave function is constructed from the basis states of the Hilbert space, and it has to be sum up to 1, normalization. Okay, so that's the language that I should speak about the system. How do I describe that my measurement could be either up or down?
If A is 1, or equality B is 0, there is not.
No, wait a minute. This is quantum mechanics. A could have a value and B could have a value. The only restriction I have until I perform a measurement. But I didn't. I'm now looking at the guy leaving here. I don't know. It's a wave function. A and B is what I can. I need an operator to describe up and down. Okay. And write down an operator that tells me in the direction of Z whether I'm up or down. Okay. I claim that we can write this operator as I could have written it in the matrix representation. Remember, an operator is a matrix. Those are both equivalent representations. Okay, what's the logic behind it? Let's play with it and see what it gives us. Okay, let's assume I add the case that you prefer it has only a component in the up direction. Okay, so in that case, psi is equal to okay, how do I write down the average?
the bra. The operator.
As I say, it's an algorithm. I don't. Once I define this, which needs a moment of thought, and define my Hilbert space, I'm just working with the definition. It might look strange, unintuitive, but that's that.
This is the end.
Psi, so let's write down explicitly. Psi is this guy, because that's what I want to see now. Here I have the operator. Okay. Let me just remind ourselves, okay, if this is a basis, what do I know about the scalar multiplication?
Orthogonal.
Orthogonal, meaning that, orthonormal even.
Yes.
That's the meaning that they are a basis.
This is by choice, right? Because it's more comfortable to work in an orthonormalized basis than a non-orthogonal basis.
Yes, why to hit your head in the wall when you have a door? Okay, so I'll write it down here in detail, probably the last time in the course. Okay, finished here. Sorry, not finished. All of it. I wrote down.
The operator.
No, I
supposed to be
wrote
of
it
the-
down.
No,
Sorry,
it's
sorry.
finished.
Finished. I'm finished.
Yes.
1, 1, 0, 0 equal 1. Okay, that's the average. I'll see always 1.
Shouldn't be minus between the 1 and 0s.
Excuse me, this is minus 1. What will happen if instead of sigma up, I'll have sigma down?
It will be minus 1.
The result will be minus 1. What will be the result if I'm taking a full?
It will have mixed terms.
Yes, let's do it again once. in order to see it in detail. Well, in this case, this is psi. So I wrote psi. Note that it's complex conjugate, and therefore I have complex conjugate on the scalars. It's important if A and B are imaginary or are a complex number, and they certainly can be complex numbers. Okay. Okay. I have here 8 different terms, but a lot of them I can throw out immediately. This is something that you'll acquire with practice. Okay, this guy times this guy is okay, because it will give me 1 here. This guy is only times this guy, because all others are 0, so it's...
You're not supposed to do the operator on the psi and...
I'm supposed to do it step by step,
yes,
but...
Trust you, you say.
No, trust yourself. Get some experience and you'll be able to do it.
Okay.
Down with this guy, not interesting. Down with this guy, interesting. So it's minus B complex. Whatever comes here with this, not interesting. It's 0 times this, so it's... Makes sense? Yes, because the average will be however many will have some probability of coming on the upside minus the numbers that will come out on the downside. This number is defined by a square times a square or b square, up and down. That's the probability of finding it up or down. So the mathematics gives us our intuitive understanding of probability. Okay, so for this system, we know everything. What do I mean by know everything? If we'll go to our screen and see that the size of this blob is the same as the size of this blob, I could say that the wave function coming out, a squared is equal to b squared. Then you can come to me and tell, well, the magnitude is the same, but perhaps they have a phase difference. And I'll tell you, okay, with this experiment I can't tell you more than that. You want to find phase. What do we do in optics to find phase?
An interferometer.
We'll need some kind of an interferometer in order to tell you what is the phase. But from this experiment, the only thing I would be able to tell you is that a squared is equal to b squared. Okay. Let's do another step here. So we introduced our Hilbert space, we introduced our experiment, we introduced our notation and calculated averages. Now I want to do something with the wave function collapse or the measurement. How will I do here a measurement? Okay, so let's say I'll replace this screen just retain the same color. And then put my screen. I'm allowed? Yes. Nobody forces me to do my experiment in a certain way. If I have enough money to buy another couple of magnets, I'm certainly allowed to stick it in the path. Okay, so what will I measure on the screen?
2 points. 2 positions. I think 4 positions because of for each split you have another 2 splits in the after the second magnet.
So you say 4. I'll see here 4 points.
Yeah.
It's maybe 4, but it's maybe.
Okay, I didn't organize a Kahoot, so let's do it by showing hands. How many of you think that there will be 4? How many? 2? So democracy works. You'll have, at home. Well, I gave the answer already, so I'm sorry. So actually, you'll measure only 2 points here. Why?
Because if it goes down, it will go down again.
So that's exactly the collapse of the wave function. It came out from here as A plus B. But here I performed a measurement. Doesn't matter that I didn't measure, but if it's with the component of going up, it will go up. If it's with a component to go down, it will go down. So while here I had no idea except for normalization what is the structure of the wave function, here I already know that if it went to here, it must be spin up. If it went down, it must be spin down. Therefore, when I'm doing the measurement here, it will be pushed even more down, but it can't end up in an up position. So you'll see here only 1, 2. And that's exactly the famous collapse of a wave function. You see that although philosophically, as you heard in the clips and as probably you read in popular literature, do I need an observer here? I don't have to look here. The fact that they will take different paths, I know what will be the component of the atoms that went that way. And although here I didn't know anything about it, I knew only that with probability a squared it will be up, with probability b squared it will be down. Here I know that with probability 1 it will be up, with probability 0 it will be down, and vice versa. So this is exactly the collapse of the wave function. Here it's this wave function, it's this wave function. It's hard to swallow. That's the heart of the Copenhagen interpretation.
Can I ask something?
Sure. Yes.
Are the measuring devices on the right side horizontal?
Yes.
They're perpendicular to the first one, right?
Both of them are in the same direction, Z. In a couple of minutes, we will rotate them because it's very interesting.
Oh, okay. But right now they are parallel to the first one, right?
Right. Both. This is in the Z direction, and these are in the Z direction, meaning that they measure the same up-down components in the direction of Z.
All right. Thanks.
Sure.
Another interesting question will be how many pass up and how many pass down, right? But that depends in A and B.
This depends here. This doesn't change it. Because if it passed, it's already down. And this is the point where that's decided.
Right.
Is there any time constraints for you to take the next measurements? If you take, let's say, after the first measurement, then you take, and we wait for 1 year, and then you make the next measurement, then things will be different.
So what happens here? Look, what happens here is, let's say the old Stern-Gerlach experiment, you have a stream of particles. They just left the screen and saw the blob created on the screen. Nowadays, you can do it with electronics. And you can do it, it's even easier and nicer, with photons. And again, a photon has polarization, so you can also do left polarization and right polarization, or doesn't matter the detail. And you can put here detectors and have a source that sends one photon each second. Nowadays, with fast electronics, you can you can measure separate measurements every 10 to the minus 12 or even 10 to the minus 15 seconds. So you can do it one by one, and then if you're sitting here, you'll see it hit once, the next one, either here or here, still half-half. Next, half-half. Next, half-half. So if you stop the experiment in the middle after 10 photons, no one will promise you that you have 5 and 5. That's the most probable case. But you have some probability of measuring 4 and 6, both are. Some even lower, 7 to 3, and very rare 10 to 0. If you measure 10 to 0, probably you should go and buy a lottery, because you're very lucky. But each experiment is independent. We know nothing about it. If along a million experiments you see all of them coming out up here, so you should go back and check if your box has a magnet in it that had aligned already your particles. Because then your assumption that it comes out in any direction is clearly wrong. Okay. So, as Eliyahu has asked at home, what happens if I measure in a different direction? Okay, so for that, I will need to know how I write the operator of measuring the moment in direction x and in direction z. Since you have chosen to live in a universe with three spatial dimensions, that's all that you have. Okay, what does it mean? Instead of measuring in this direction, I tilt it 90 degrees. In this experiment, I won't be able to measure y because it's not in the direction of it's exactly in the direction of progress, but in principle can change the setup and also measure in direction. So what is sigma x? And I'll wait a minute with sigma y. Okay, let's see if it makes any sense. If I go and measure and have the wave function in the direction up in z direction, what do I know on the magnetic moment in the x direction? You know nothing. Let's see that that's the result that we'll get. Okay, so we know. So we write down the average. Shut up and calculate. Okay, this guy times this guy is 0, because it's down times up. This guy remains. Okay, because it's up times up, it's equal 1. So I have here
down, and then up, and up, that's 1.
So this is 0. The average is 0 because I didn't perform any measurement in the x direction, although I'm sure that the spin in the direction of x is up, I know it has the same probability of being in any direction of x, either plus x or minus x, and the average therefore is 0. Now you hit your head on the principle of uncertainty. Although you know z completely, the magnetic moment in the z direction, you know nothing about the direction, the moment in the x direction. But how can it be a classical spin has x, y, z components, right? When I'm going to a quantum description, I can fully determine it in one direction. I lose any information on the remaining two directions. We'll define the uncertainty principle in details, but this is a very good example of the uncertainty principle. You have heard it about position and momentum, but the same here, same principle.
Experiment. No.
So I measure it in the z direction, I know nothing in the y direction. So Eliyahu, I take this same setup exactly, but I rotate the position of the magnets to measure in the x direction. So this is rotated. How many points I'll measure now?
4.
4. Because although I know here that it's in the z direction, I know nothing about where is it in the x direction, and therefore I'll measure here 4 points. Not here and here, but there'll be, okay, think of it as 2 points here and 2 points here, separation in the x direction.
How the particle goes here and then
Here it's
goes into the magnet.
and then it has a magnetic field here in the x direction, and that will separate it to 2 different directions. Although here I knew everything that could be known about the z direction, I know nothing about the x direction. And if I stick here some combination of, let's say, 45 degrees, so I can write down the operator as sigma x plus sigma y, 1 over square root of 2. And I can give you a prediction how much I'll measure in one direction and how much I'll measure in the other direction. Here it won't be equivalent because I have a z component that I know something about, the y component and x component that I know nothing about. But still you'll have 2 points, but unequal in size. So that contains the whole all the interesting stuff about quantum mechanics in a nutshell. Everything else you'll see is just elaboration on these principles. It's new, it's unfamiliar, perhaps unintuitive, but are there questions?
I don't understand. I understand why there is 4 points. I don't understand why they are there.
And not? Where do you want the 4 points to come in?
When the particle goes like this, it
Okay.
gets into between the magnets, right?
It goes in. If it had, here a measurement is performed.
Yes. It's up or down.
It's up or down.
Right. Then
The
it goes-
X component, I know nothing about.
So when we measure the x component, the sigma x operator will change to the form of sigma z operator.
You can't think about it as rotating your bases. That's the reason that it's written this way. I didn't want to go into details because we didn't yet discuss how do you rotate bases. But that's all there's to say. But once I measured it here, and now let's come, and I put another measurement in the z direction, again I know nothing about the x direction. I know everything about the x direction, I know nothing. So I went in here knowing everything about z direction. I come out from here knowing everything about the x direction. But if I measure after that, I still will know nothing about the z direction. Because each measurement collapses the wave function. Now the wave function will be an eigenfunction of the x operator. And this eigenfunction is not an eigenfunction of the z direction. Therefore, you have a probability of measuring it in either z up or z down. Each time you measure, you have a new wave function, and you have. So, I didn't intend to do it, but let's do it. Results of a measurement are the eigenvalues of the operator, and it collapses into the eigenvector corresponding to that eigenvalue. So if you know if you want to know what you can measure, you should know the eigenvalues and eigenvectors of this operator. Okay, how do you do a eigenvector and eigenvalue? You come and say, if I operate sigma z on some wave function, I should get psi times
And I get
lambda, whatever you choose to call. Lambda has to be real.
right. Since it's
And
almost-
here I know there are only two eigenvalues because my dimension is 2. All this is linear algebra. Okay, so I could write down the matrix. Tell you immediately. Okay, guys. It's 1 with okay. Okay, I could use the bracket notation, say sigma z times and I'll get write it down in detail. Okay, so the definitions. So we see the only way that this will be equal to this if either A equal 1 so it's this guy with lambda equal 1, or if B is equal minus 1. If I have a B equal 1, A equals 0, and the eigenvector is minus 1. No other combination will work. So it's B equal 1 down with lambda equal minus 1. Okay, so that's the explanation why I told you this is for up, this is for down, because up corresponds to the eigenvector in the up direction, down corresponds to the eigenvector in the down direction. Okay, what happens for sigma z, sigma x? This was almost trivial. Right at the first. Do I have to show it in detail? Don't be ashamed. Towards the exam, I will expect you to be able to diagonalize a 2x2 matrix. But at the moment, if someone needs a demonstration, okay. Just multiply this. Just, what does this do? Just switches up and down. So this will be the same. So lambda is equal 1. This will go opposite to minus 1, 1. And therefore the eigenvalue will be minus 1. 1 over square root of 2 is to give me a normalization. That's all.
And we can now express those vectors in terms of the other vectors, right?
And I could have written this. Let's show that it works with the other definition of sigma x, with the bracket. So I want to take sigma x times move the 1 over square root 2 outside. Up, down, plus, down, up, plus 1 over square root 2. 1 over square root 2 moved outside. Okay? This time this is 0, this time this leaves me with just up. This times this time this down, this time this is 0. Okay, so it's an eigenvector of sigma x with
Richard,
of 1. Yes.
at the start, okay. So all of this is under the assumption that the Hilbert space is of dimension 2, right?
Right.
And also that it's of finite dimension. Does it follow from some postulate?
If it's 2, it's as finite as it gets. 1 is trivial, right?
Yeah. Like, is there a way to guess that too from the postulates of quantum mechanics that doesn't rely on experiment?
No. Physics is an experiment.
I mean specifically on this experiment. It's like,
no, I have to know something about the world. Otherwise, I can come up with, no, the world has 26 directions and an atom has a spin of 1,000,002. I can't rule that out. It's like you'll come to me and say, could you prove that mathematically that the world will include electrons? No, I don't know how to prove it. Physics has a very good mathematical grounding, but mathematical grounding without experiment, you have a lot of things that can work. We have few things that really work in our world, and the way to deduce them is experiment. So you can see by eye immediately what is the probability for an eigenvalue of x to measure spin up?
1/2.
1/2, because it's the amplitude square. Down 1/2. So therefore, I know that I'll have 2 points because I measured here an eigenvalue of z, took it here, and I ended up with an eigenvalue of x. In eigenvalues of x, I have equal probability of measuring either x or minus.
And actually, it's interesting because now you are sure that you have half in the right and half in the left, right?
Right. After this measurement,
You don't
I'm
care
sure.
about A and B.
No. And You remember perhaps it's the beginning of the postulates, even in the beginning, what did I say? You have initial conditions of wave function, and you work with the Schrödinger equation, and you know if this is a wave function at time t0, you'll know what will be the wave function at time t. From where do you know the wave function at time t0? If I perform a measurement and can separate the different results of the measurements, I know that the wave function is the eigenfunction of this operator. And that's my initial condition. So that's how I get an initial condition. I tell you, well, let's prepare a bunch of particles with spin up. And you ask me, how do you do it? Here, that's how I do it. I take a pulse of them, pass them through a magnet, and use only those that came out on that position. Then I know the wave function. So the answer, what is the initial condition? How do I do it? Perform a measurement. Well, it's not so surprising. Also in classical physics, how do you know initial conditions? Because you saw it there. I know that Mars will be tomorrow here because yesterday I saw it somewhere before. Otherwise, just giving me the equations of the Newtonian motion doesn't tell me where I'll see Mars. Same here. Wave function is determined by measurement. It's a good point to stop. After the recess, we'll run into an initial problem. First of all, we'll define mathematically when do I, after performing a measurement on one operator, when do I know something and when I know nothing about a measurement of another operator. In this case, we saw I know nothing, but there's a mathematical quantification of what I know. And then we'll start treating the more familiar operators, position and momentum, and there we'll run into some mathematical problems regarding the fact that they're infinite. We'll see how we treat them. So, just before the recess, we have shown that if we know the result of a measurement in the z direction for a spin half particle, we don't know what's happening in the x direction and vice versa. If I have two operators, if I'm given two operators, how do I know if these two operators can be measured simultaneously? If I know one, I know something about the second, or if I measure one, I know nothing about the other. So the mathematical procedure for checking that is the commutation relation between these two operators, and we'll see why. So, if I have two operators A and B, my statement is if the commutation relation between A and B, which is defined is equal 0, then it can be measured. Okay, what is the source of this statement? Okay, what does it mean that I measure operator A? According to the postulate of quantum mechanics, I have a basis of eigenvectors of A, in which if I operate on psi I with operator A, I get the function times a constant, which is the eigenvalues of A. Okay, let's assume that I performed this measurement. And then I come and measure B. So, every psi I, which is the result of the measurement, that's what I know about A after the measurement, the collapse of the wave function, has to give you a distinct value for B. So it means that this basis follows also this relation. I operate on psi I with B. I get some value of BI, which doesn't have to be equal to AI. But still, each vector here is also an eigenvector for B, meaning that the basis of psi I is the same basis for both operators. Otherwise, I measure some value of A, which gives me a psi I, and this psi I is not an eigenvalue of B, so measuring B will have some probability of coming out with one result and some probability with another. Therefore, after I measure A, I don't know definitely what are the values of B. Okay, now I'm left with just proving this mathematical statement that if it's the same basis, the commutation is 0. Okay, let's check it directly. So I have a okay, let's take the first term and operate on some wave function. Any wave function in my space, I can build a superposition of the bases. Okay, so and I can, of course, choose the basis of operator A. But since it's also a basis of B, I can write down because it's a linear operator, I can use it on each one of the components, get out the eigenvalue, and this appears here. But these two are scalars, numbers. So I can now operate with A. Now let's go through the same game with the second term in the commutation. Trivial. But this is equal to this because in multiplication of scalars, AI times BI is equal to BI times AI, and therefore, if they have the same bases, the commutation relation must be 0. I won't prove here the other way around. If we have a commutation relation that is equal to 0, we can write down to the bases that will belong to both operators. But it's almost true. Okay, so if I have two operators, I know that the commutation relation is not 0. I know you can't measure them. If you measure one, you don't know necessarily everything about the other. We have met a couple of such operators, x and p. We did this calculation xp, and we showed it's not equal to px. Therefore, they are not commutating. Therefore, you can't measure both of them in the same time. Okay, but truth said, we didn't calculate the eigenvalues nor the eigenvectors, not for x and not for p. So we'll start by doing it for x. Hopefully, maybe we'll also do it for p. If not, we'll do it in the next lecture. So if you want, we're jumping here from the easiest case, n equal 2, to the hardest case, x which has an infinite number of possible measurements. At least we believe this to be true. Okay, so what we're doing now is so what do we demand? You operate with the operator x on psi, which is an eigenvector of this operator with eigenvalue x0. It will give you x0 times the same wave function. Sounds trivial. We can expand it to talk about three dimensions, and then it will give you, as a result, psi is a function of x. And if x is equal x0, should be give us a value of 1. Should give us a value of 0 anyway, any place that is not x0. This is
why 1? Exactly 1?
because it's there. That's the measurement, right?
Ah, alright.
It's here, it's not there, it's not even close to here, it's not epsilon for you. It's here. That's
It's like delta function. It's delta function.
okay, you jump ahead, but you see already the mathematical problem. It's not a continuous function. And this is a mathematical problem. We're trying to talk about differential equations. Everything that we're doing in Schrödinger's equation is continuous, derivatives, all kinds of nice things. This is not a nice thing. And this will create some problems that we'll have to shock the mathematicians by solving it.
Because it's not even in Hilbert space, right?
Right, it's not in Hilbert space because Hilbert space has to be continuous. Composed of continuous functions, and basically physicists were walking around the world were for a couple of years till Dirac told them, don't worry, I'll redefine what's normalization. And you can't, it has even a problem of normalizing. And the third one is told them, look, I'll redefine for you normalization, don't worry about it. Life would be infinitely simpler if space would have been discrete. Then no problem at all. And it's all good. Okay. So you use the term delta function. You were supposed to get a bit of a background about delta function exercise. I'll briefly go over these properties. Mathematical definition. And note that because of density, because I'll perform a summation over a continuous variable which would be x0, I need their infinity because it's density. So this is a bit naive and not exact. And I'll continue to be not exact. So what do we know about a delta function? And I'm at the moment in one dimension. As long as within your range of integration you have 0, the result of the integral is 1 because the rest of the integral is a summation of zeros.
You wrote that A needs to be lower than 0 and B upper because
if
it would be
it's
minus 1, right? No?
Yes, but I don't want them both on the same side because then it's 0.
Because it's x, not x minus x0. Yes.
Right. If I would have written x minus x0, then I have to be above and below x0.
Yes. Thank you.
And if it was x minus x0, it would have been f of x0. Okay. Some properties of delta function. Zero everywhere except for 0, so
Right.
okay. How do I treat delta of A times x?
1 divided by
1
absolute
divided by
A
U6
delta.
of A.
So always when you have to, you're at a problem in understanding what are properties of delta x, stick it into an integral where the operators, where what you're doing to delta x is well defined, and see what you get. So if I'm looking on the integral don't know, but I can replace AX
No. We need to be the absolute value, right? Of A.
Yes, wait a minute.
ביטל הוא אבסולוט. מוחלט.
Because of this, it doesn't, you have to have that AX is equal minus AX, and therefore I have the absolute value. And this I know how to perform. So I can write down okay, let me write a few more properties. Where f of x I has 0, f of x has zeros at xi. Same idea as before. For example, so x squared minus a squared could be written as x plus a x minus a, has zeros at a and minus a. And if I write down this definition, I'll have here x plus a plus delta x minus a, and I have here 1 over
Why this 1/2a is important?
Because I want
it's
that
go-
integration will
will be
get
one.
to 1.
Yes, normalization.
Everywhere else, whatever goes into Gx is not interesting. Why the only place that it doesn't go to 0 is if the two deltas sit one on top of the other. In a moment, I'll show you well, there's all kinds of asymptotical definitions of delta function, taking an asymptote of some form of delta. I found that one of them is much more useful than all the others. I write all the others, but refer only to the last definition because to my taste it's the only one you really need. All the others are correct, but they are just harder to manipulate. And truth is they never appear in quantum mechanics in any case. So why are all these definitions useful? Because they enable you to operate within the well-defined definitions of quantities and taking the limit only in the end. So less chances to make mistakes. So you take an exponent and take epsilon to 0, which leaves you with a finite value only at x equals 0. All others you have here infinity. Don't understand why it's written down, because this is an ugly function. It has absolute value, and we know that we don't like to work with absolute values in general. again, very loosely speaking, the only place that, again, it's limit of epsilon going to 0. Only place that this is not 0 because of this guy is at x equals 0. And this normalization of the integral to be 1. Again, it's 0 anywhere when epsilon go. All of them are limits of epsilon going to 0.
That one is kind of an infinitely peaked Gaussian, right?
This is exactly an infinite peak Gaussian, and if you remember the integral of a Gaussian, you have square root of pi, therefore you have here divided by square root of pi in order to normalize it to 1. Okay, this is an interesting function. It has mathematical niceties. I don't want to go into it. You see that it goes and becomes, the oscillation becomes denser and denser as you go to 0. It's a nice function mathematically. Again, I don't want to go into it. Actually, well, I will go a bit into it. I thought that I can perform a shortcut, but I need it for the end definition to make it much easier. And first of all, let's see that it goes to, what do I need? The basic quantity, to integrate and show it's 1. So, limits of epsilon going to 0, 1 over pi minus infinity till infinity, 1 over x sinus x over epsilon. Let's just change variables. Instead of an integration on x, I will perform an integration on y equals this guy, x over epsilon.
It's y epsilon in the. No.
No, I have here y dx and 1 over x kills the epsilon.
Why do we use 1 over y?
Because I had 1 over x. I just
alright.
substitute, nothing clever here. Instead of
epsilon
x, I'm
multiplication.
writing epsilon y. Instead of dx, I'm writing dy over epsilon, and
Yes, multiplication.
that's it. Okay. How do we perform this integral? Someone has an idea?
Yes, we got that.
Hmm?
Integration of parts.
Parts won't help you.
Yes.
You'll move from a sine to cosine. You don't know to do a sine. You don't know to do the cosine. Here, complex analysis helps you. That's why I thought about leaving it out, but it will be helpful in 5 minutes. Okay. So, in the complex plane, this is x, this is y, and z is x plus a1. Okay, you're looking worried. You haven't learned it?
It's in Memphis 4. Should be in the next semester.
Okay, so I should have skipped it. Someone here does know complex analysis, so I'll give it 3 minutes for you. This is the integral. So sorry about the y here, it's not.
Okay.
Okay, this is the integral from here to here. Like always in complex analysis, I want to integrate over a contour.
Right.
I'll close it like this. Why? Because sine somewhere in the 8th.
2y
Right.
2y
and minus.
yeah, a minus is important. Okay, so every time you lose this, you move from this plane, you have here a negative exponent. Meaning if you take this contour closing up to infinity, and that's what you need because your integration goes from infinity to infinity, this path doesn't contribute anything. Where is your, so you have to just identify poles.
Right. At 0.
And there's only one pole here in a nasty place at 0. But at this point, it's nasty because it's on the contour of integration.
Right.
So what do? You take a small circumference around it and take it to 0 at the end. So you have no pole, for this thing, you have no poles inside.
Right. And then you can use Cauchy theorem.
Exactly, and then you use Cauchy's theorem and you end up with 1 here. Because you have, from this thing you get just pi.
Right.
Okay, so for those of you who have some knowledge of complex analysis, it helped. For those of you who don't have, it didn't help. But what is very important, and that's I'll use a lot during the following course, is, well, if you accept that this is a definition of a delta function, and I've shown the integral is equal to 1.
It's supposed to be x divided by x.
Divided by x, sorry. Why? Perform the integral. It's a very easy one. Need help? E to the power ik is 1 over ik e to the power ik. Put in the boundaries, you'll get sinus, and that's it. Why is that so important? Basically, and this is the only thing I really want you to remember of all the definitions, because that makes life extremely easy. Epsilon is going to the limit of 0, so the integration is between minus infinity and infinity. And again, this is something you'll see in different parts of your courses, in solid state, for example. It's a more concise way of writing it down, because k vector dot r vector is kx, x, ky, y, kz, z. Exactly what's written here. Okay, so I have all I'll need to know about delta function in this course. Okay, as I said, for me, this is the only definition of delta function I really want you to remember. Okay, so let's go back. I claim that delta function is the eigenvector of the position operator. Let's see if according to all that we have learned, it fits. Okay, so x that works okay. So, yeah, sure. Certainly an eigenfunction of x. Do I have an orthonormal basis? Okay. For it to be an orthonormal basis, let's write down the definition. Integral. Just again, working with the definitions. A scalar multiplication is integral over x. It's not finite, it's not a summation, it's an integral. Delta of x minus a times delta of x minus b. We have seen it. Works wonderfully. Okay. Delta function is not 1. If you remember, we have seen it in the beginning.
Right.
We asked the value to be 1 and ended up with a delta function. We can't escape it. If we use a delta function, this is the definition. So, what do we do here? We defer to Dirac that told us if it's continuous, this is good enough. So it's instead of being orthonormal, it's being Dirac orthonormal, which simply means, which states the same. And not 1. So this is Dirac. Okay. It's a detail, but we have to pay attention, and the bigger problem here is that delta is not within our Hilbert space, because it's not continuous. Okay, if you think about it a minute, basically if you look on physics as an experimental science, well, you never can define a position in a continuum. You can give around the point. You're always missing an infinite number of digits in defining the position.
So you have a big enough Gaussian, right?
So usually you take it with a grain of salt. You write delta, and basically you say, I've measured it within some epsilon, and then go back to all the definitions that have epsilons in them, or ignore it completely and work with the Dirac's orthonormality, and nothing, and at least on this level, nothing bad happens. Okay, now to end this lecture, we'll finally understand why merely we write down psi of x for the last, since modern physics, when we told that all the time you have to expand your wave function as a sum over superpositions of the basis states. How does one go with the other? Well, very simple. At psi of x. Yes, that's how we write a wave function since the beginning of the course. But we told it's a sum over the eigenvalues of some operator. We chose the position. Position is continuous.
So we have to perform it.
So instead of a sum, we have an integral. Well, now I'm integrating over variable x prime. A of x prime, say A of I, delta x prime minus x, this is my position, right? So when I write psi of x, I write the amplitude that comes before the delta belonging to the wave function. And we forget this whole story and just write psi of x because we're working in the basis of x. And we know the probability of measuring some value I, it's I squared, Therefore, the probability of measuring x is a of x squared equals which we knew all along without this whole complex language, but until now you may have come to the mistaken conclusion that for all other operators I have to write the amplitude of the eigenfunctions, and for position I have a special psi of x. No, I have nothing special. Just the expansion of the wave function in this basis. Okay, so we'll do momentum in the next, and then start to translate from one description to the other, from one basis to the other.